Today, we will be talking about a very interesting technique, which is again extremely useful in optimizing a lot of algorithms. So today, we are going to talk about contribution technique. But before we talk about contribution technique, I'll get started with a very simple question. And actually, that is a prerequisite for you to learn this technique. That's a question, simple question. Let's say there are three cities, Delhi, Bombay, and Chennai. Okay. So let's say there are three different roads which are connecting Delhi to Bombay. And there are two different roads which are connecting Bombay to Chennai. So of course, if let's say currently you are in Delhi and you wish to reach Chennai, you have to take one of these three roads so that you can go to Bombay. And then you have to take one of these two roads so that you can land at Chennai. So let's give these roads some names. Let's say this is National Highway 1, this is National Highway 2, this is 3, this is 4, and this is 5. If I ask you a very simple question, that hey, in how many distinct ways can I reach from Delhi to Chennai? Then what will be your answer? When I say distinct way, I basically mean a distinct combination of roads. How many distinct combination of roads can you take so that you reach from Delhi all the way to Chennai? So here, yeah. So here, if you're looking carefully, there can be multiple ways of reaching. One way could be you take road 1 and then you take road 4. Okay. On the other hand, you could also have taken, you could have taken road 1 followed by road 5. You could also have taken road 2 followed by road 4. So all in all, how many ways are there? So a lot of you who have answered it, you have said that there are 6 ways because you are saying that from Delhi to Bombay, there are 3 roads. So there are 3 ways. And from Bombay to Chennai, there are 2 roads, so there are 2 ways. So you're saying that your answer is 3 into 2, which is 6. Now, this thing is a very basic rule of product. Have you heard of it? How many of you have heard of rule of product? This is a very simple rule which is taught in our combinatorics classes. Wherever we study it, in class 11, 12, or in college, we are taught uh, the rule of product, right? It's the very basic thing of permutation and combination, right? So why is this rule of product valid? So first, let's understand that it's very simple to understand, guys. See, uh, I can say that there are three possibilities to go from Delhi to Bombay. I could either have taken road 1 or 2 or 3. So I could either have taken 1 or 2 or 3. And in order to go from Bombay to Chennai, I could either have taken 4 or 5. Now, one possibility is you club 1 with 4 and then you get this path, which is 1 comma 4. Or you club 1 with 5 and then you get this combination, which is 1 followed by 5. The same thing could have been done when you club 2 with 4, 2 with 5, or 3 with 4, 3 with 5. So if you are really taking a look over here, this is just like a Cartesian product. This is just like a Cartesian product where I can say for every road that I take to go from Delhi to Bombay, my next set of choices to go from Bombay to Chennai are 2. So if let's say there are M roads over here and N roads over here, then for every road that I take, there are N choices here. So for all the M roads, total number of choices will be M into N. So, the basic thing is that if you are performing any compound action, which is accomplished by performing action 1 and then action 2. Now, if for performing action 1, there are X different ways, and if for performing action 2, there are Y different ways, then total number of ways for performing this action will be X multiplied by Y. Okay. Now, there is one very important thing over here that both the actions must be independent of one another. Independence is very important. So what I mean by being independent, see, regardless of which road you took for going from Delhi to Bombay, you will always have two choices. to go from Bombay to Chennai. So what I actually mean by that is, let's say you took road 1. Now it doesn't mean you can't take road 5. You can always take road 4 as well as road 5, right? Similarly, if you took road 2, again you can take 4 or 5. So your choices for action 2 are not a function of your previous choices, are not dependent upon your previous choices. So that has to be true. If that is not true, if both the actions are not independent, then this rule cannot be applied. So this is a very, very important thing to understand. Just take this example. If somebody says that, hey, if you are coming from highway 1, you cannot take highway 5. So if that is the rule, I cannot do 3 into 2. Because when I am doing 3 into 2, I am by default considering 1 comma 5 also as a combination, right? So I can blindly do this rule of product only if both the actions are independent. So far, all that we have learned is rule of product. What is rule of product? That is already written over here. Now for rule of product to be valid, the important thing is that all the actions must be what? Independent of each other. Okay? Okay, it was just a bit of combinatorics around it. Okay, let's move on. So now going ahead, okay, it's a common thing. I mean, many of you might even know about it. So we'll solve some questions and you will again be able to relate, just in case if you did not relate at this point of time. So don't worry. Okay, now let's take a quick question. So let's say we have an array containing some integers. So let's say it has 2, 1, 4, and 3. The question is very simple. We want to find the sum of all the subarrays of this array. So we want to find the sum of all the subarrays of this array. What is the meaning of subarray? Subarray means array inside an array. So let's say this is an array. Inside this, there are so many other arrays, and subarray has to be contiguous. That is very important thing. By contiguous, I mean you can say that this thing is a subarray 1 comma 4, but you cannot say that 1 comma 3 is a subarray because 1 comma 3 is not contiguous. Yes, this entire thing is a subarray. 1 comma 4 comma 3 is a subarray, right? So can you tell me one thing? Just answer one thing first. Let's say there is an array which contains n elements. How many subarrays will it have? And I'm talking about, obviously I'm talking about non-empty subarrays. How many non-empty subarrays will be there if an array has a size of n? Okay, so one of you is saying 2 power n, and then one of you is saying n minus 1 by 2. You see, this quantity is very, 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 very large, and this quantity is quite small compared to that. And then we have one more answer, n factorial. Okay. Okay, so let's take a look and understand. See, it's very easy to reason about it. It's quite important to be very, very clear about these small things. Okay, see, if there is an array, I'm just listing down the indices 0, 1, 2, so on till n minus 1. See, every array has a starting point and ending point, right? So let's say whenever you consider any subarray, it has a starting point I and ending point j, right? Now, if I ask you, hey, how many subarrays are there whose starting point is at 0? So the first array whose starting point is at 0 is just this, which starts at 0, ends at 0. The next one is this, which starts at 0, ends at 1. Then starts at 0, ends at 2. Then starts at 0, ends at n minus 1. So how many total subarrays are there which are starting at this point and ending at either 0 or after it? How many such arrays are you able to see? There are n of those, right? Because if the starting point is 0, the ending point could be 0, the ending point could be 1, the ending point could be anything from here to here. So there are n choices. Now, how many subarrays are there which start from here? So if the starting point is this, the ending point could be this, or this, or this, or this. So there are n minus 1 such subarrays. And how many subarrays are there which are starting from here? If you go by the same logic, n minus 2. Finally, how many subarrays will be there which start from here? Only one. And what is the sum of this thing? It is the sum of first n natural numbers. 1 plus 2 plus 3 so on till n. And what is the sum of first n natural numbers? What is the sum of first? Did you study it in your class 10th or somewhere? Yeah, it happens to be n plus 1 divided by 2. So these many subarrays are there. Okay, now let's come back to the original question. So what was the original question? That we have an array 2, 1, 4, 3. Okay. And for this array, I want to find the sum of all the subarrays. Sum of all the subarrays. So it basically means you should first list down all the subarrays, find out their sums, and then sum up all those sums. So I literally want to sum up the sums of all the subarrays that are out there. So let's do that. Can you see some subarrays that it has? Like first subarray is this, the second subarray is that, the third subarray is this. In fact, there are so many subarrays, right? So I have to list down the sum of all the subarrays and then I have to take the final sum. So this is a little long arrays. We'll take a little short one so that it's a little convenient for us. 2, 1, 3. Can you tell me what will be the output for 2, 1, 3? Okay, so for 2 and 3, the first subarray is this, whose sum is 2. The second subarray is this, whose sum is 3. And then we have this, whose sum is 6. And then we have this, whose sum is 1. And then we have this, whose sum is 4. And then we just have this, whose sum is 3. What is the sum of all these values? 2 plus 3 is 5, plus 6 is 11, 12, 16, and 19. I hope it is 19. How many of you are getting 19? So if you're getting 19, you're getting the right answer. Okay. Now, how do I solve this question? Let's start from the brute force way of solving it. So see, the brute force way could be to simply consider all the subarrays. How many subarrays are there? You just listed them down, n into n plus 1 by 2, which is approximately n square. So if you have to list down all the subarrays, you can very easily do that. You can say that, hey, let's write a nested loop. I goes from 0 to n minus 1 and j goes from where? I to n minus 1, right? So this is your starting index and this is your ending index. And then for all the subarrays, you can just compute the sum and then you can keep on adding those sum and that is how you'll get your answer. So this approach will cost you n square. Can all of you code this approach? Yeah. Okay. Now this approach will give you a TLE if your n is anything around 10 power 6 or 10 power 5, it will give you TLE. So can I do something better? So that is where the content of today's class will make things feel very interesting. So, contribution technique. What it says is that, hey, instead of listing all the subarrays, why don't you consider contribution of each element? See, what do I mean by contribution of each element? This is a very important point. So let's focus on this. Let's say you had this array, 2, 1, 3. I'll rewrite it here. 2, 1, 3. Can you tell me how many subarrays contains 1? So this array had so many subarrays, right? Out of those subarrays, how many subarrays contained 1? So I can say, hey, this was a subarray which contained 1. This was another subarray which contained 1. This was another subarray which contained 1. And this was the final subarray which contained 1. So if there are 4 subarrays which contained 1, then what is the contribution of 1? The contribution of 1 is 1 multiplied by 4. Can I say that? Yes or no? Right? Similarly, how many subarrays contain 3? This subarray contains 3. This subarray contains 3. This subarray contains 3. So if there are 3 subarrays that are containing 3, the contribution of 3 will be nothing but 3 into 3. So I can say contribution of an element A of I is equal to A of I multiplied by the number of subarrays that it is a part of. Now, all that we have to do is we have to somehow calculate this thing. Can I calculate this thing pretty quickly? Is there a way I can pretty quickly find out that, hey, how many subarrays would be there which will contain a particular value inside it? What if we have duplicate number? No issues. Not at all. There are no issues around that. Why? Because we are interested in considering all the subarrays. I never told you that you do not have to consider subarrays that are unique or something like that. You understand my point? So let's say you have something like 2, 1, 3, 2, 1. So one subarray is 2, comma 1. This subarray is also 2, comma 1, but both of them are different, right? This is different than that because clearly the starting and ending point of this is different and starting and ending point of that is different. So I'm not worried about what duplicates are there and not. Nothing like that. I'm just interested in, considering all the subarrays and finding their sum and summing them up. Okay, let's focus our attention on the major part, which is this. How do I get to know how many subarrays an element is going to be a part of? So listen to it very carefully because this is the most important point. This is the heart and soul of what we are discussing. So let's say you have an array which is like 3, comma 1, comma 2, comma 4. Now, if I focus my attention on 2, and I want to know that how many subarrays will contain 2 inside it, then you know what I can say? I can say that, hey, if you consider any subarray whose starting point is one of these 3 elements and ending point is one of these 2 elements. For example, let's say if you consider a subarray whose starting point is this, okay, and ending point is that, then of course this is going to contain 2. Similarly, if you consider a subarray whose starting point is this and ending point is that, then that also is going to contain 2. See, this 2 is the intersection of this and that. So it means that, hey, if you consider any subarray whose starting point is one of these and ending point is one of those, it will definitely pass via this 2. Is that making sense? How many of you are able to understand this, right? Okay, you can just take another example. 3, 1, 2, 4, 9. Just think of it in this manner. Imagine all these numbers are just like cities. This is Delhi, this is Bombay, this is Agra, this is Jaipur, this is Bangalore, something like that. Okay. Now, if I ask you that, hey, I want to build roads connecting the cities. So how many roads will pass through this? How many roads will pass through this? Common sense says that any road which starts from one of these cities and ends at one of these cities will definitely pass through this. Is that now making sense? Why? Because this is the intersection. This is the intersection of this and that. So if you're building any road which connects this to that, it will pass through this. Maybe connecting this and that, it will pass through this. So what I can say is that for picking my starting point, how many options do I have? There are 3 options. For picking my ending point, how many options do I have? I have 3 options. So 3 into 3 is 9. So it basically means that there will be 9 subarrays in total, which will be passing through this 2 for sure. And thereby the contribution of this 2 will be nothing but 2 multiplied by 9. And you can see that in action. You can see that in action over here. Let's say this is 2, comma 1, comma 3. Okay. You want to consider the contribution of 1. Let's say you want to consider the contribution of 1. Can I say that any subarray which starts at this or this and ends at this or this will definitely pass through 1, right? I can definitely say that. So how many options do I have for choosing my starting point? 2. And how many options do I have for choosing my ending point? 2. So 2 into 2 is 4. So there are 4 subarrays which will contain 1. So the contribution of 1 will be 1 multiplied by 4. Similarly, if you're talking about the contribution of 3, let's say you want to talk about the contribution of 3, you would say that, hey, any subarray whose starting point is one of these and ending point is just this, it will contain 3. See, starting point here, ending point here, or starting point here, ending point here, or starting point also here and ending point also here. It will definitely contain 3. So for starting point, that you had 3 options. For ending point, only 1 option. So total number of option is 3 into 1, which is 3. And so the contribution of this 3 is 3 into 3, which is 9. Is that making sense? How many of you are clearly understanding? Okay. Now, if I have to generalize it, the most important thing is to generalize whatever we talk about, right? So if you want to generalize, some of you have already done, that's amazing, that's awesome. So let's say that's your array, okay? And this is your index I. And you are interested in the contribution of A of I. So can I say that any subarray whose starting point is from 0 till I and ending point is from I till n minus 1. Any such subarray whose starting point is from here to here and ending point is from here to here will pass through it and thereby it will contain this. So tell me, how many options do you have for starting point? From 0 to I, how many options are there? I plus 1. It's not I, it's I plus 1 because the starting point is 0. So I have got I plus 1 options for my starting point. And how many options do I have for my ending point? It is n minus I. So there are n minus I options for ending point. So how many subarrays will be there which will be containing this element? I plus 1 multiplied by n minus I. And mind it, I told you that this thing is independent of this thing, regardless of what is your starting point, whether your starting point is this or this or this or that, you can always have n minus I ending points, right? The choice of ending points doesn't get influenced by what starting point you choose. Whether you chose this, you still have these many points to choose from as your ending point. Or you chose this, you still have these many points to choose from as your ending point. So these many choices for starting point, these many choices for ending point. So this into this is the total number of subarrays which will be passing through it, and thereby the contribution of this element will be this multiplied by A of I. Now the job is done. So if I know the contribution of each element, I can find those out and I can keep adding those, and that would be my answer. So now the solution to this has become pretty simple. So all that you would have to do is you would have to run a for loop. You would say for I equals to 0 to n minus 1. And what would you say? Answer plus equals to, just use that formula, which is I plus 1 multiplied by n minus I multiplied by A of I. What is the new time complexity? Order of n. Because this loop is just running for n times, and every time we are just doing constant work inside this. See, just to sum it up, the simple idea is that instead of listing down all the subarrays, we wanted to consider contribution of each element. This technique is also called as reverse lookup. Certain people call it like that. It basically means that instead of doing what has been told, you do reverse of it. And thereby you obtain some optimization. So instead of listing down all the subarrays, you focus on one element and try to figure out that, hey, by what amount this is affecting my answer. So if you have to do that here, you need to know how many subarrays will contain this. And how many subarrays will contain this? For exactly same thing, we did this much of work and we came up with this thing, multiplied it with this, and the job is done. So did you get the idea of contribution technique? This was the simplest question. So did you get what's the key idea behind contribution technique, everyone? Okay, that's very good. Now, if you have to implement it, if you write this code, there is one major thing which you will face. And what is that? You will get integer overflow. You will definitely get integer overflow. Why? Because you are doing so many multiplications and then you are adding. Just imagine, if you have an array which contains very large numbers, 10 power 6, 10 power 7, very large numbers, and then there are so many of those, right? So it may happen, in fact, it will happen that the answer might not fit inside an integer. So in such questions, if you read the problem statement, the question says, the last line of such questions, you might have read such questions on Code Forces or HackerRank or LeetCode. It says that, hey, please return answer modulus some number, some special number, like let's say 10 raised to power 9 plus 7, something like this. Have you seen these kind of line added to the last line of your question? Yeah, you would see it. If you have not seen it, you would see whenever a question is, asking you to solve a problem where the answer might be huge. Now, computers cannot store infinite size numbers, right? They can only store numbers till certain size. So in order to check whether your answer is right or not, the problem statement says that, hey, take the modulus of your answer, because if you take modulus with something, if you take modulus of something with 4, the result is always lesser than 4. It is either 0 or 1 or 2 or 3. All of us know that, right? So see, here we will have to use modular arithmetic, right? So how many of you are aware of modular arithmetic, what it is? So that is another prerequisite for coding it. So I'll touch base upon the rules of modular arithmetic. We will not dive deep into the proof of those rules, but I'll tell you that what exactly is modular arithmetic and what is the utility of it. So just tell me one thing. In the childhood, you have studied that a plus b multiplied by c, it can be written as a multiplied by c plus b multiplied by c. Have you read it? Yes or no? Yeah? Okay. What is this? This is distributive property. Distributive property states that this multiplication can be distributed internally. So you distributed it over A and B, as you can see, right? Now, is the same distributive property applicable for mod also? What do you think? If somebody says, I want to do A plus B mod C, can I write A mod C plus B mod C? What are your thoughts? So if you're confused, if you're not sure about it, then you can even try it out. You can try it out and see what happens if at all you try to do something like this. Okay, so let's take a quick example. If let's say you have to take 5 plus 4 mod 9. Okay, what is the real answer of it? Tell me. What is the real answer of it? 5 plus 4 is 9 and 9 mod 9 is 0. But if you follow this distributive rule, what will you get? What is 5 mod 9 and what is 4 mod 9? 5 mod 9 is 5, 4 mod 9 is 4, and you will get 9, which is nonsense, right? Because when you are taking mod with 9, the result should always be smaller than 9. So, so the rule says, again, I'll not go into the proof of it, but the rule says that take one final mod also. Take one final mod again with 9. So it basically says A plus B mod C has to be written as A mod C plus B mod C whole mod C. As simple as that. And the same thing is true for multiplication also. So if you want to do A multiplied by B mod C, you have to distribute. First, you have to distribute. Okay. You have to do A mod C into B mod C. And then you have to take one final mod with C again. Right? For subtraction, okay, for subtraction, there is just one small caveat which I would touch base on. So let's say you want to do A minus B mod C. Okay. Now here you have to be just a little careful about one thing. So you can definitely distribute. You can do A mod C minus B mod C. You can do this. But at times this value may become negative. Don't you think so? It can easily become negative because this quantity might be larger than that quantity. You can take some example if you'd like to take that. So let's say you are doing 9 minus 7 mod 4. Okay. What is 9 mod 4 and what is 7 mod 4? 9 mod 4 is 1. 7 mod 4 is 3. The result is minus 2, which again is nonsense. But what is the real answer? The real answer should be 9 minus 7 is 2 and 2 mod 4 is 2. So the real answer should be 2. So if your result is negative, if result is negative, you just have to add C to it. Because what really happens is, if you are getting this negative result, it is just shifted from 0 in some direction towards the left, minus 2. And if you perform a plus 4 of it, which is this, the number that you are taking mod with, it is immediately shifted towards this side. Okay. We will prove it someday, but for now, just understand that if you are taking A minus B mod C, this is the rule, take A mod C minus B mod C, and if the result is negative, just add C to it. That's it. And for addition, it is quite simple. For multiplication also, it is quite simple. So this is the rule that we will follow. This is the rule that we have to follow if we want to be able to write the code to, to get, to basically implement this thing, whatever we have learned. Now see, if you want to write the code for this, you will have to perform everything that you are doing in a modular arithmetic manner. So this multiplication should be done using modular arithmetic. The multiplication of the result of this and this should also be done using that. This addition should also be done using that. Okay. Even 1 minus 2 mod 3. Yes, everything. I mean, when you have to, I mean, whenever you encounter situations like these, where you have to add two numbers and take a mod, let's say you have X and Y, and you have to do this, follow that rule. Minus, multiply, whatever. For division, you cannot. For division, you cannot follow this rule. For division, there are different concepts of totient rule and all that we'll probably talk later. But for now, this is, the key, the basic idea of modular arithmetic. So I'll show you some code. I'll show you some code towards the end of the class where operations would be done using it. But for now, if you understand this thing, that's good enough. We'll just move ahead from here and we will quickly turn our problem from one dimension to two dimension. So far, we had an array. Now we will have a matrix. So it's a 2D matrix containing some elements 2, 1, 1, 1, 2, 3, 3, 3, 1. Let's say something like this. Okay. And now, can't we convert negative to positive? That is what happens here, right? Just see, the moment you add C to it, the result will become positive because this negative quantity, the negative quantity that you get over here will never be lesser than minus C. Just think of it, because in the worst case, this will be 0 and this will be C minus 1. So in the worst case, it can be minus C minus 1. So if you add C to it, it will be thrown at 1. So automatically it pushes it towards the right side of the number. Okay. I mean, the same thing. What is the difference between that? I mean, whether you write it like 9 plus minus 7, it's the same thing. You have to deal with this negative thing again, right? How do you deal with this negative thing? So, yeah, so exactly you can follow that. So this is the matrix, and what we want to do is we want to find the sum of all submatrices. So in the last question, we were finding the sum of all subarrays. Here we want to find sum of all submatrices. What is submatrix? Submatrix is matrix inside a matrix. Okay. So for example, this thing is a submatrix. Okay? This thing is also a submatrix. This little thing is also a submatrix. This thing is also a submatrix. So there are so many different submatrices. So for each of those submatrices, I want to find their sum, and then I want to sum those sums. Okay, please do not say that this thing is also a submatrix. No, this is not a submatrix. Submatrix has to be rectangular, right? It has to be some rectangular thing. So you can definitely call this thing as a submatrix. You can call this thing as a submatrix. You can call this thing as a submatrix. So there are so many submatrices, and those sums we need to compute. Okay. So first question is, how many of you got the question? Yes or no? So let's take a very simple test case to verify if we understood it. Let's say we just have a 2 cross 2 matrix, 1, 1, 1, 1. Can you tell me what will be the answer for this? Yeah, this whole matrix is also a submatrix of itself. Just like how a complete array is a subarray of itself, a complete matrix is also a submatrix of itself, obviously. Yeah. So what is the answer that you guys are getting here? So let's see what are the submatrices that we have here. So first submatrix is probably this, just one element inside it. So one. Second submatrix is this, one, then this, one for that, then this, one for that. What else do we have? We have this one, this, right? What is the sum? 2. And then we also have this. What is the sum here? That's 2. And then we have this huge one, this big one. What is the sum? 4. 4 to 6 to 8. 8 plus 4 happens to be 12, right? Are we missing out on something? The vertical ones. Correct. So we listed down this. Let me just use this. We listed down this. We listed down this. We listed down this and that, right? You can see those, correct? And then we listed down this. We also listed down this. But then we did not list down this and this, right? So for this and this, the contribution of plus 2 and plus 2 will come again. Plus 2 plus 2. So it will become 12 plus 4, which is 16. So your answer will be 16. Is it clear to everyone how the answer is 16 in this case? Yes or no? So what can be the simplest way to solve this question? After 12, what you have done? We have just considered the contribution of missed out matrices. So just see, like what are the submatrices that are out there. So I'm just highlighting them again. This is the first one, okay? That's the second one. That's the third one. That's the fourth one. And then this is the fifth one. This is the sixth one. And now can you see the vertical ones also? This and that. And finally the complete one. So just list down their sums, take the sum, you'll get 16, right? So yeah, one way is to list down all these submatrices and then solve the question. But if you list down all the submatrices, the time complexity will be very high because there are so many submatrices out there. So can we do something better? Just think in terms of contribution. What does contribution technique says? That somehow try to figure out the contribution of each element. I mean, each element, just look at each element and try to figure out that how many submatrices will be containing that. So let's focus over here. Let's say you have a really big matrix like that. Okay, just keep looking here because this is the most important part. Let's say you want to find the contribution of this element, the element right here. So let's say the element over here is 5. And you want to know that how many submatrices will contain 5 inside them. Is there a way to know that quickly? So for that, let's put our attention over here. See, how do I denote a unique submatrix? Let's keep looking. Let's just take any random submatrix, any random submatrix can be identified by top left and bottom right, isn't it? If you fix your top left and bottom right, you get a unique submatrix corresponding to that. So if somebody says that, hey, the top left corner is maybe 2 comma 2 and bottom right corner is 5 comma 3. What is 2 comma 2? 2 comma 0, 2. This is 2 comma 2. This itself is 2 comma 2. And what is 5 comma 3? 3, 4, 5, 5, 0, 5, 1, 5, 2, 5, 3. This. So basically 2 comma 2 and 5 comma 3 is denoting this particular submatrix. So all that I'm trying to say is that, yeah, all that I'm trying to say is that a submatrix is denoted by a specific top left and a specific bottom right. Okay. Now tell me one thing. If you consider any submatrix whose top left is chosen from one of these cells, the top left is chosen from one of these cells. Okay. And the bottom right is chosen from one of these cells. For example, let's say the top left is this and the bottom right is that. Then what is the submatrix that you are considering? The submatrix that you are considering is this. And does it contain this 5? Yes. The answer is yes. I can tell you that any submatrix whose top left is chosen from one of these cells and bottom right is chosen from one of these cells will definitely pass through this cell. Why? Because it is an intersection of this and that. You just consider anything that you want to consider. Let's say your top left is this and bottom right is that. So the submatrix that you get is this. And this contains this 5 inside it. You take any other example. Your top left is this and bottom right is that. So the submatrix that you get is this and it contains 5 inside it. Obviously it would consider. Obviously it would contain because this is the intersection point. Is that making sense? How many of you are getting this idea? Okay, so what does it mean? It means that now just tell me that how many choices do you have for picking your top left? Like in this case, how many choices do you have for picking your top left? There are 9 different choices. And how many choices do you have for picking your bottom right? 16 choices because there are 16 cells. So how many combinations do you have? 9 into 16. So I can say these many submatrices will contain 5 inside them. So the contribution of 5 will be this thing. Does it make sense? Any submatrix can be created by top right and bottom left also. That's a very good question. Yeah, of course. And I'll touch base on that. I'll touch base on that. See, I'll tell you one very simple thing. The moment you choose your top left in this part and bottom right in this part, let's say this is your top left and this is your bottom right. As a consequence of that, uh, as a consequence of that, the submatrix that gets considered, that submatrix has top right in this part and bottom left in this part. So it automatically happens that all the submatrices that will be considered, they will be having their top right because currently you were talking in terms of top right and bottom left. I was talking in terms of top left and bottom right. But if you want to talk in terms of top right and bottom left, then also I am open to it because all those submatrices that I get from here will definitely have that their top right in this part and bottom left in this part. And of course, they would also be passing through it. So whether you go this way or that way, the count will be the same. Okay, I'll touch base on this point once again towards the end. But for now, the most important thing is to generalize. Yeah. Let's generalize this count. It's pretty easy to generalize now. So let's say you are interested in I comma j. You are interested in the contribution of I comma j. So I can say that our starting, I mean, our our top left could be any of these cells and our bottom right could be any of those cells. So how many choices do you have? How many cells do you have in this part? So if this is I comma j, then what will be the length of this? Considering it starts from 0, the length of this will be I plus 1. And what will be the breadth of this? J plus 1. So how many cells will be there in this? The number of cells in this will be I plus 1 multiplied by j plus 1. Do you understand this thing, everyone? Similarly, can you tell me the number of cells in this? Let's say the dimension of matrix is m cross n. If the dimension of matrix is m cross n, what will be this height? It will be m minus I. And what will be this breadth? This will be n minus j, right? So what does it mean? It means that number of cells inside this will be m minus I, sorry, it will be m minus I multiplied by n minus j. See, simple enough, no? I mean, if you are interested in finding the contribution for this element, then how do you do that? You say that all those matrices whose starting point is present in this part. By starting point, I mean top left is present in this part and bottom right is present in this part. It will definitely pass through it. This is the assertion that you give, right? So now you just have to find out how many cells are there in this. That's a very simple question, because if this is I comma j, this square, or sorry, this rectangle will have dimension I plus 1 into j plus 1. Why plus 1? Because indexing is from 0, not from 1, right? So the number of cells in this part is this. And with the same logic, the number of cells in this part is m minus I into n minus j, where m is the number of rows and n is the number of columns. So I can say the number of choices for top left is these many. And the number of choices for bottom right is those many. So what is the total number of choices? The total number of choices, very good, will be product of this and that. And what is that product? It is I plus 1 into j plus 1 into m minus I into n minus j. So I can say that, hey, these many submatrices will contain this element. So the contribution of this element will be A of ij multiplied by this quantity. This is the contribution. Is that making sense to everyone now? This was the long formula that many of you were typing who knew how to solve this question, but is that now making sense to all, that where from this comes? This is contribution of this element. So this is the element and this is the number of submatrices that contain that element. So this product is just contribution of this element. So now all that you have to do is, now there is nothing much which is left. So you can just iterate on all the elements. I equals to 0 to m minus 1, j equals to 0 to n minus 1. And then you can just update your answer. And for updating your answer, you can just use this formula. So what is the complexity now? Order of m into n, right? Because this nested for loop runs for m into n time, and every time you are doing constant work, you are just multiplying some integers. Of course, you will have to use modular arithmetic, because here the chances of integer overflow are very, 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 very high, because you are doing so many different multiplications, right? So that you will have to take care of. Okay, what was the initial complexity? This I comma j could be the part of bottom left and top right matrix. So it should be, no, that's what I'm telling you. See, okay, so some of you are asking this question. So let's face it. Some of you are telling me that, hey, what you did made sense, but what you ended up saying was that, hey, if the top left is in this part, top left, let me write it, top left, and bottom right is in this part, bottom right, then such matrices, such submatrices will pass through it. This is what I said. I said and I ended. But now some of you are saying that, hey, how about the reverse of it? The reverse of it is that if I consider top right in this part, so top right in this part and bottom left in this part. For example, if your top right is this and bottom left is this, then the submatrix under the consideration is that. So this will also pass through it. Is that making sense? Yes or no? So the one who is saying this is saying that you should take into account for such submatrices also, whose top right is in this part and bottom left is in this part. What I'll reply to it is not needed, because those would automatically be taken into consideration over here. Why? Because you just create that matrix whose top left is this and bottom right is this. That matrix would be this. Now, this matrix would automatically have gotten considered when we would have considered top left as this and bottom right as that. Because any submatrix whose top right is in this part and bottom left is in this part, that submatrices top left would be in this part and bottom right would be in that part. So if you consider this, you have already considered that. Is that making sense? Yes or no? And you will see that even if you go by what you are saying, you will get exact same formula. I tell you, you will get exact same formula. Because now if you are, let's say, focusing on top right to be in this part, sorry, the top right to be in this part, then how many cells are present over here? This dimension will be m minus j, it will be n minus I, sorry, it will be n minus j, and it will be m minus I. So from here you will get that the number of choices is m minus I into n minus j. And if this thing is I comma j, then here the number of choices that, sorry, not m minus I into, it's just a little muddled up. It'll be this particular length. If it is I comma j, this will be n minus this number of columns is j. So you can figure that out. It will either be m minus I into j plus 1, and here it would be n minus j into I plus 1. So basically, if you do a product, you will end up getting the same thing. If you do a product, you will end up getting the exact same thing. Okay, you can try that out. So both ways are the same, whether you go by this or that, it kind of works. Okay, cool. So does that make sense? Do you understand this variation in 2 dimension? Yes or no?